Okay, we go over the last session, and in this session we will describe how each step in this one is actually performed. But I will give you a quick overview of that by going to the page number to the page number 28. This is how exactly it's done in terms of computation. Actually, this parameter, this I superscript t plus 1 is equal to tau jk. But you will see why we would use this I. I is like a, you can think of it as like a one hot vector that will take zero value where you don't select the elements. For example, if you want to select element of a vector, let's say you call it vector x, right? And it has 1, 2, 3, 4, 5, 6, 7. You have 7 elements in x, and you want you want to kind of enable some of these values to be selected or to be shown. Sometimes people will multiply this in a dot product way, not dot product, in a point-wise manner with, let's say, a one hot matrix, which will take value 1 on the element that you're interested in and 0 to the rest. So in this case, you will get the new vector that has a value of, let's say, x1, x2, and 0 for the rest. So that is the one hot vector. I'm just trying to tell you that this is the kind of element that you will get. This I here is actually like a one hot vector or one hot matrix for you. But usually the way it works is like that. If it's a matrix, then it will be a matrix that selects parts of your part element in your matrix such that it's non-zero. That's what it was. So yes, in this case, we kind of use it to replace tau jk parameters. And once you have this value here, then you use it to compute an expectation. And this expectation is actually like a loss function where you will solve this loss function for the model parameters, which in fact we have like a closed form formulation that you can just plug in this closed form formulation. And here, notice that you use the I t plus 1 from here. So this I t plus 1 is actually your tau. So you could probably remember that, yeah, it's like in previous step, we get this tau jk before, right, from the parameters that we estimate, or maybe that if we randomize it. But after that, this tau jk will be used as part of the estimation for the model parameters. And as you can see, it's actually hidden inside the closed form formulation as well. So yes, you can replace this I t plus 1 as tau jk, like that one to be tau jk, that one tau jk, that one tau jk, as well as this one. So yeah, so it just resonates with what I mentioned earlier, but in this time we will see how things happen this way. Yep, and actually we call this kind of algorithm expectation maximization. But you will see why we call it that way. But as a hint, as you can see, we compute something called expectation here. Sorry, just this sum of expectation is expectation. And maximization is where you solve the maximum likelihood here. Yep. Okay, let's start it. Okay, first of all, okay, before that, I call this maybe vector or matrix as like one hot vector, but in this case, it's like cluster assignments. It's like it would take value 1 if that particular elements fall into a cluster. For example, if you think about your x here, right? Let's say if you only have a scalar x, let's say if you have only scalar, so that means x1, x2, up until maybe x1 10,000. This is all your x, right? And your I or cluster assignment will be the one that assign value 1 if let's say they are in the same cluster, and value 0 if they are not belong to that cluster. In this case, if it's belong to a particular K cluster, then they'll be highlighted as 1. So we have this element so that we don't need to do the exact sorting. So I'll put this way, this is like a trick in computing when you have a very long vector and you only want to select only few non-zeros, yet you don't want to really sort each element. So normally people will come up with assignments, vector or matrix like that. Yep, right. Okay, so let's go to the beginning. Right in the beginning of everything in Gaussian mixture model, actually, thing is, if we can just estimate the model parameters in Gaussian mixture model, that is pi k, mu zk, and sigma zk directly, there's nothing you need to do. I mean, there's nothing else you need to do. You only need to find a closed form formulation to update these model parameters, and that's it. But the thing is, as you will see, when we try to estimate these model parameters, you will end up with a formulation that has an unknown parameters, that is the I, the one hot vector, that you can't really do anything about because it's there, but you can't really, you need to estimate it before you can compute these formulations. So you have to kind of keep identifying what this value could have been. So that's why expectation maximization take place in this situation. Okay, so yes, right in the beginning, we will first find, so if we want to estimate these model parameters given our input xj, we can do it by solving maximum likelihood, and in this case, we will do it to the joint probability between x and z. We already know that's actually, the multiplication between pi k and pop of x given z, right? And because, okay, you probably maybe wonder, then why there must be multiplication over here? The reason is because when we solve for parameters such as this case, we need to first considering the joint probability of everything in our scenarios, and that everything including all the clusters, all the cluster, which is the first one, all the cluster, and the second one is actually for each element in each cluster, or maybe for each sample in a cluster. In a cluster, and this one for all clusters. So that means if you compute the joint probability by multiplying all of these, they should be representing the joint probability of all data samples that you're considering, and these data samples are your training samples. Okay. And once you have that, because it's the products of probabilities, the easiest way to address this is actually to turn this problem into a log space. So you take the log, and that product will become a sum of log. And once you have the sum of log, the thing is, if you look at this summation, it's actually selecting each samples in a cluster. That means you have to sort for each cluster and find which sample are in maybe cluster number 1, which sample are in cluster number 2. But you know that these samples can overlap between 2 clusters. And for that, you can actually use a one-hot vector to identify them. So that one-hot vector is this I vector. And this I vector is in output this way is like a binary 0, 1, size n. Let's say if you have not n, maybe m. If your x is xj, j equal to from 1 to m. So this is like a one-hot vector that select each of the samples in your training to the one that's supposed to be in your cluster. So if you have x1 up until xm, and you, let's say, want to select the first sample, maybe the second and third, like that, but you only want to select these 2 to be, let's say, cluster number 1, you can actually have like this I matrix equal to 1, 1, and the rest is 0, right? So then it can select just 1, 1, and the rest is 0. You don't need the rest. So that means you can now, making the summation that is as if it was before, but this time you don't need to sort for each of the cluster. You just use this I vector or this cluster assignments vector to select which xj will be in that particular k cluster. So in this case, as you can see, I can now extend from j in k to j equal to 1 to m, because I have this I vector that can pre-select. Okay, so if I select this just like that, so that means if I multiply these 2 point-wise, what I would get? I would get just x1 and x2, right? So the same for the probability. If you multiply this I vector with the probability of, let's say, xj equal to 1, okay, given that, pop of xj equal to 2, given that, and so on and so forth. You can use this I to compute the point-wise product, and then it will select only the element that you're interested in. So that's the key idea. Is that okay? It's kind of like that. Anyway, after you have this formulation, the next thing is, as you can see here, summation from k equal to from 1 to k. So as I mentioned before, if it has summation like this, and if you have that, it's equivalent to marginalizing. But this time it's marginalizing with this I vector, which behaves like a pi k. It's like a weight of that log, right? Because it's sum over that. So it is as if you are computing, because this time, this time, this one is not a pure probability, it's a log-up probability. Therefore, it turns into an expectation of that log. You can just go back and try to write down. And you can think of this as a probability. So now you have your loss function that is look like a sum of expectation. So, if we would just future forward to that expectation maximization, as we mentioned before, expectation maximization has a phase where you have to compute expectation. So it's kind of like fitting the card where you have to compute a loss that has this expectation term. And you need that maximization to solve for these model parameters. But bear with me. We will go over that. Okay. I think the very mysterious thing is about this term that we will try to decompose, because actually this term will give you the closed form formulation for your model parameters update. So that's kind of the reason why in the next slide we will go over decomposing this part. Okay, so in here I think you just breathe in and breathe out. Thing is, it's simple as that if you are decomposing the joint probability, that joint probability to the original form where you have log of x given z times the pi here, and then all you need to do is substituting the Gaussian distribution inside prop of x given z, because we said before that we want this probability to be the Gaussian distribution. And this one is like is a weight. But yes, again, everything is currently weighted with that I. But we will ignore it for now. Just know it's part of the formulation, but we will not focus on it. When we decomposing probability of x given z, we can use Gaussian formulation. But the thing is, if you look at this formula and imagine that you have to estimate this covariance matrix, this is highly difficult, especially if you have matrix in combination with the depth and you have to compute. When you do maximizing or minimizing, you have to compute the gradient of the depth, which will give you so many procedure. You have to find adjacent, stuff like that, which is extremely difficult. That's the reason why people may assume this to be, let's say, just an identity matrix or a matrix with equal, an I's matrix as well, like when every element has its own distribution. Yep. So, but maybe the simplest one is to assume the same variance for the time being, and then you have this formulation. But notice that this variance, sigma k, when you have sigma subscript k like this, it simply means that you are intending that each cluster will have different variance. But the sample in the same cluster will have the same variance. And this one will be much simpler to solve than the original, like a full formulation of the Gaussian distribution, right? So next thing, once we have this formulation done, we just put it together to this original formulation, which result in this one. just move forward with that. I think you can go back and try to iterate whether or not it's true. And once you have this equation, this means you have exactly your loss function, right? Where all the model parameters are kind of decomposed in a way that if you need to take gradient with respect to each any of these, it will be simpler. So yes, we will write it again. That is this one. When you have this formulation and you want to estimate the model parameters, what you have to do, because it's actually a concave function and argument max, definitely everything here, when you take the gradient and consider that as at the stationary condition, they should give you like the optimal value that will maximize your loss. So with that, you can take gradient with respect to each model parameters, just like in here. But keep in mind that whatever loss function do you have above here is actually equivalent to this one. Here I just wrote it so that you know that actually, like if you have to compute this, you would know that each element came from this one. In next slide, we will go over the detail about how to compute the differentiate, like the taking the gradients. Okay, like this one taking gradient with respect to mu, this one taking gradient with respect to sigma, this one taking gradient with respect to pi k. In fact, I think this one, I'll put it this way. If you look at this one, this is a closed form formulation that you get after you take a gradient. It's a sum of xj, where j is iterate within that particular cluster. So that means you can use that I vector to select the non-zero, right? And you can sort from j equal to 1 from 1 to m. And then below here, you can just sum over the non-zero, so that will be equal to the number of the number of samples within that cluster. And next one, okay, you compute the sigma k at the stationary condition. Same thing happened, like when you try to compute this and equate it to 0, you will get some kind of formulation which you can use this I matrix, I vector, to decompose each of them. And then at the end, this is a formulation that you get for the variance. I think this, you don't need to pay too much attention, it's just a formulation. Okay. But lastly, this is the one that's trickiest. Because if we look at the log of pi here and you take a gradient and equate it, it just turned out that pi can take pretty much any large value. But in fact, there are some constraints because this pi k is like a probability, so the sum of it has to be equal to 1. So in here, I just extend the loss function a little bit to include this constraint. And in fact, with that, you will get something like, if you solve for, you use these Lagrangian parameters and just find the infimum. Sorry, not sure if it's supremum or infimum. But anyway, you will get this pi k equal to 1 over lambda plus beta minus gamma. And all of these are Lagrangian parameters, which are greater than 0. And that means it just, okay, any value between 0 and 1. That's what it all means. It doesn't really have any particular meaning. Therefore, people normally resort to estimate the pi k with the number of non-zero coefficients in each cluster as a ratio to the total number of samples, which kind of makes sense. If you think about, if you have, let's say, 1,000 samples, and the chance that this cluster would exist depends on how many coefficients are there within this cluster. So that's kind of like, at the end, they decided, okay, maybe it's best to estimate these parameters based on this estimation. And it's not really defined by any Lagrangian or any optimization, but it's just particular one, because when we solve for Lagrangian, it just show that you can't really have any better formulation. It's just this one that's kind of like the best for it. Okay, so at the end, we have the closed form formulation for all of the unknown parameters, right? But unfortunately, if we think about this I matrix, it's like a pre-selecting matrix that's selecting each samples into a cluster. Like, how can you know this if you don't know what is the center of that cluster, what is the distribution of that cluster, what's the weight of that cluster? You can't know it. So the problem is, as I vector is unknown, and that's kind of the reason why we need some iterating mechanism to estimate this I vector and re-estimate the model parameters. Once you have a better model parameters, maybe you will get a better estimation for each I vector. So that's kind of the reason why it goes this way. And yes, part of it is because when we look at the loss function, there are expectations inside it. That's kind of like two reasons to combine into why at the end people say that, when we estimate the model parameters in Gaussian mixture model, we will use what we call expectation maximization. Because first, you have the phase where you compute expectation, and second, you have the phase where you compute the model parameters by solving the maximum likelihood. And this expectation is part of the cost function in maximum likelihood, which fit to our situation. Yeah. Just look at it roughly. Honestly speaking. Don't go to, I try to explain, but yeah, everything here is like giving you a rough idea of how things come. And to apply expectation maximization into our setting, yes, first, there's loss function that fit the cards. Like you have the loss function that has expectation as part of it. Second, you have these cluster assignments that is kind of like an unknown that you need to keep iterating it. And this cluster assignment is representing a tau value, because it's, like selecting whether or not this sample belongs to this cluster, this sample belongs to this cluster. But it's kind of like resembling this mechanism of tau jk. It's not exactly tau jk, but it's like a mechanism that resembles it, therefore we use it to represent tau jk. Finally, since we have to estimate the tau jk, we know that once we have the model parameters, we can re-estimate the tau jk again. So everything here put together as the following algorithm. Yep. So that tau jk equal to pi k times x given, pop of x given sat. After that, once we have tau jk, we can compute the expectation. And actually, with the randomized or initialized model parameters, we can plug in and calculate the loss function. Once we have a loss function and, parts of model parameters, then we can update them with these maximum likelihood formulation. Solution of the maximum likelihood. And finally, just future forward to this. This is exactly what it looks like. If you look at, visualize each update step. But yeah, this is how things came from in terms of how we actually apply expectation maximization. I think what you have to keep in mind is to not confuse between tau jk and pi k. At times it could be quite confusing because let's say there's no precise way to estimate pi jk, but just keep in mind that pi jk, because it's representing the probability of that cluster existing, so that's why we use this average, or maybe this ratio between non-zero coefficients in that, not coefficients, non-zero samples, particularly in that cluster. Yeah. And that's it. And if you want to look at this in a more precise way, I have actually provided the coding for you. This is exactly how E step and M steps are computed. And set here is in fact the that tau JK. And if you click into this link that I attached, you will go to this GitHub page where you actually have this, like a visualization of how the algorithm progressed and the fact that the log likelihood of your function will start to converge when the algorithm performs steadily, estimating the model parameters and everything. So this is like as your side notes because we don't have the lab. Therefore, I provide a code for you to kind of go back and try it. Yep, so today you have 2 algorithms in hands. I'm not sure if that's going to be useful for your future, but I am very sure that we all be very, yes, it's a lot today. But anyway, that's the last session. Please let me know what will be your available time for your final exam. And just to confirm with me, the 30th of April will be a good time for a quiz session. Yeah, the quiz session will be very similar to last time, as in it will be like a choices. I wasn't sure